SS-99, Wake Vortex upset. Unclassified, Director Mr. Slade, 4 March 76.
Flegel's problem was my problem not too long ago. I was flying the F-4D, number 3, in a 4-ship formation. As I rolled out on final, I encountered mild turbulence. The buffeting stopped momentarily, and then about 700 feet above the ground, I encountered severe wake turbulence. My bird rolled rapidly to the right, about 90 degrees, nose low. I thought I about had it whipped when it rolled right again, and the nose went down another 20 degrees. In spite of trying to roll back, the bird stayed in that death spiral. I hit full military power, then the AB. I'd almost rolled back when my right wing caught a 70-foot high tree, which was 1/2 mile from the end of the runway. I managed to go around, but my right burner blew out. My nose gear indicator showed unsafe. My leading and trailing edge flaps also showed unsafe. And I lost my utility hydraulic pressure. Oh yes, my right generator went off the line. But I was still flying. I used emergency gear extension and configured for an approach and barrier engagement. I touched down at 160 knots, about 500 feet short of the first barrier. No engagement. I deployed the drag chute and used emergency braking to keep the bird on the runway. We engaged the second barrier successfully. I want to tell you, for a while there was some real white-knuckle flying. The Accident Investigation Board found the aircrew did everything right except for one thing. Severe wake turbulence was encountered, which rendered the aircraft momentarily uncontrollable. The sheer power of wake vortex, its tornado-like intensity, it's pretty scary stuff. It's even more of a hazard because it can't be seen. If it could, it would look something like this model. These trailing vortices, which spiral back from both wingtips, are capable of flipping any aircraft on its back. Any aircraft, regardless of size. And if it should happen to you as you're preparing to touch down, you can see the danger. We asked the aeronautical engineers to define wake vortex, and they gave us this. It's a well-ordered swirling flow of air generated because of the lift exerted on the wing. This means a powerful swirling cone of air is generated and comes off each wingtip, extending in the wake of the aircraft for several miles. And therein lies a danger or hazard. However, it is predictable as to location and magnitude. These vortices can persist for a long time behind the generating aircraft, up to 3 minutes, sometimes longer. The swirling air may exceed a velocity of 100 miles per hour for some aircraft. They're still very strong, 10 miles behind a jumbo jet, and are capable of inverting a fighter or trainer in less than 1 second. The whole wake vortex problem received dramatic emphasis by the crash of a T-38, which ended in 2 fatalities and the loss of the aircraft. A reconstruction of the accident showed that the crash occurred approximately 5 seconds after the T-38 encountered the vertical wake hazard. The T-38 was in the process of performing a tack-and approach prior to landing behind a stretch C-130 transport that was making a VFR landing. Although the T-38 pilot and the air traffic control personnel were operating within all applicable directives, the T-38 closed to approximately 1 minute behind the transport. The different types of approaches used by the 2 aircraft put the T-38, while still 2.5 miles from touchdown, below the flight path of the stretch C-130. The vortex caused the T-38 to bank with the left wing down at an angle greater than 90 degrees, despite the efforts of the pilot. This was immediately followed by a rapid decrease in altitude. As the pilot tried to regain a wings level attitude, the aircraft crashed. Analysis later showed the roll moment exerted by the vorticity field of the C-130 exceeded the aileron authority of the T-38 by at least 200%. There was no way to keep the T-38 wings level following this encounter. Present air traffic control directives provide increased separation to certain fighter and trainer aircraft when an approach is made behind a heavy aircraft. By definition, a heavy aircraft is one that weighs over 300,000 pounds. The stretch C-130 that caused the fatal accident only weighed 130,000 pounds, so you can see that there is an actual danger from other than heavy aircraft. That brings up another point. There's a misconception that wake vortices are only a threat or hazard to small aircraft. Nothing could be farther from the truth. Watch this. This film was supplied by NASA from a research program they have going at Edwards Air Force Base. Using smoke generators fastened to different types of aircraft, they can make the vortices visible. They can also test the effect as other aircraft fly into the vortex. Watch what happens to this C-9 aircraft, which is no small bird. The FAA has conducted a series of tests on the effect of wake turbulence on various types of aircraft. To make the vortices visible, they put smoke generators on various towers. After the aircraft flew by, they created vortices that become visible. As you can see, the vortices are literally horizontal cyclones or tornadoes, and they pack the same kind of wallop. If you fly through it, you could overstress your aircraft or possibly even upset and crash. These FAA tests teach us a great deal about the strength of wingtip vortices. Another thing to notice is that these vortices came off each wingtip in opposite directions, counter-rotating. The vortex spins clockwise off the left wingtip and counterclockwise off the right wingtip. So directly behind the aircraft, there's a strong downward force, which can be bad news for light aircraft. On the other hand, if you're close enough behind the leading aircraft, it would be possible for one vortex to lift one wingtip while forcing the other one downward, causing a roll or upset. Crossing the vortex perpendicularly causes a strong updraft, downdraft, then updraft in a small fraction of time. This, coupled with the sheer power and strength of the vortex, can give even a large aircraft a severe pounding, possibly even structural damage. When the generating aircraft is taking off or landing, the vortices descend into a ground effect and then move outward at about 5 knots. However, a 5-knot crosswind will tend to hold one vortex on the runway, where it may cause a hazard to other aircraft. The other vortex will move at about 10 knots across a parallel runway, should there be one. This could present a hazard to aircraft landing there if it's within 2,500 feet. Here we see as the vortices of the jumbo aircraft stretch out. They descend at the rate of about 500 feet a minute and level off at about 800 or 900 feet below the flight path. In clear, smooth air, wake turbulence may persist for some time. Atmospheric instability, however, hastens the breakup of the vortices. The strength and power of a wake vortex is inconceivable to anyone not familiar with the dynamics of this phenomenon. The scientists and technical people, the aerodynamic engineers, tell us that the strength of the vortex is a function of the wingspan of the aircraft, the G-loading, the aircraft weight, and the true airspeed the aircraft is flying. Here, they've written it out as an equation. Now, this formula can be used to compute the vortex effect for any type of aircraft. The equation has also revealed some facts about the magnitude of these vortex effects that are difficult to accept, but nevertheless true. They show that significant vortex hazard occurs at different speeds and various altitudes, depending on the type of aircraft and the maneuver. But surprisingly, the significant vortex hazard for most aircraft is not encountered at high speed, but at low speed in a 1G or level flight environment. For example, during landing. First, the turbulence gets worse as the speed of the generating aircraft decreases, and heavy, slow, clean aircraft pose the worst problems. Second, The hazard is greater because your aircraft is more vulnerable during a low-speed landing. The aircraft is vulnerable because it has less control authority. Or to put it another way, it takes larger movements of controlled surfaces to produce a response. Therefore, you have less maneuverability. In addition, since you're close to the ground, you have less airspace to effect a recovery. The diagram shows how the upset hazard is directly related to the circulation generated by the wing. Circulation is defined mathematically right here. Circulation is not to be confused with the airflow over the wing, which causes lift and allows the aircraft to fly. But as that airflow produces lower pressure at the top of the wing and higher pressure at the bottom, the pressures try to equalize, resulting in a rotary airflow which departs near the wingtip as a vortex core. These vortices can occasionally be seen as wingtip condensation trails behind fighters in high G maneuvers. As you know, weight is both the weight of the aircraft and its load. It is also a product of G factors. For example, if the aircraft pulls a 4G maneuver, then it weighs 4 times as much. Another factor or variable is the airspeed, but contrary to what most people think, the slower the airspeed, the more circulation that occurs. Mathematically, it's easy to see, as the right half of the equation is a fraction. The smaller the bottom number in a fraction, the larger the results. Theoretical aerodynamics gets pretty complicated, but the point pilots should remember and understand is that as the aircraft ahead of you reduces speed for landing, the more circulation increases over his wing. That gives greater magnitude to his vortex and greater danger to your aircraft, and also, of course, to you. Still looking at the mathematical aspects of the equation, you might think that since the wingspan is also on the bottom of the fraction, that the greater wingspan would lessen the circulation strength. But a larger wingspan also means more lift, and therefore a larger aircraft that can carry more weight. And that means a greater number at this part of the equation, and then a greater result here. So, one rule of thumb to put into your head: the larger the aircraft, the bigger the payload it can carry. The larger the vortex, the larger the area it affects, and the more danger to you. That's not to say that a small aircraft cannot create a dangerous vortex. Using this same formula, you can prove that an F-4 aircraft at 350 knots and in a 4G turn can create a vortex equal to that generated by a C-5 in 1G flight. Since a 4G turn is not usual in the landing environment, there's less danger of ground impact. However, it's something to keep in mind when you get into aerial combat maneuvering. Encountering a wake vortex while you're in a high-speed turn is something you're not likely to forget in a hurry. You don't need to learn how to use this equation, but you should be alert to the possible consequences of encountering wake vortices of various magnitudes. Computations invariably prove that the hazard is much greater than expected, so you must know where they occur, when they occur, and how to avoid them. All right, let's look at these models, diagrams, some selected film and slides, and see if we can't make the vortex visible or nearly visible to you. We'll talk about the effects of wake vortex in 3 different environments: takeoff, in-flight, and landing. We'll not only try to make these vortices visible to you, but we'll hammer home one thought over and over again: avoid wake vortices. Early in flying, you learn to stay out of cumulonimbus clouds, thunderstorms, because of the violent reactions and forces inside. Hitting a wake vortex in the wrong circumstances has much the same effect. The force of these horizontal cyclones is strong enough to flip any aircraft. An aircraft flipped near the ground without room for recovery or ejection can mean injuries or death. So stay out of wake vortices. The first environment we'll consider is the takeoff environment. There are several factors to be considered. Are there any aircraft taking off or landing on your runway? Also consider parallel runways and intersecting runways. You already know present procedures call for a 2-minute separation between taking off aircraft and a 4-minute separation behind jumbo jets. But don't depend on the tower to inform you. Double check your own separation. The wake or vortex turbulence is a product of flying. That means it doesn't start until an aircraft rotates on takeoff and will quit when the nose wheel touches down. For added safety, watch the aircraft taking off ahead of you and note the rotation point. If he's heavy and you're light, he will probably have a longer takeoff roll than you'll need. So if you can take off before his liftoff point, you'll be above his vortex during your liftoff and climb out. When you take off behind landing aircraft, again, note the touchdown point. His vortex will stop there, so hold your aircraft on the ground until you're beyond that point before lifting off. Although harder to see, watch for traffic on any parallel runway, less than 2,500 feet from your runway. A vortex normally drifts laterally about 5 miles per hour. Crosswinds blowing toward you of 5 to 10 miles per hour can make your vortex reach you even sooner. Crosswinds above 20 miles per hour tend to break up the vortex. Aircraft either landing or taking off on an intersecting runway can also cause a wake vortex, which will affect your takeoff twice. First, as you intersect the near vortex drifting toward you, and secondly, as you intersect the far vortex drifting away from you. The first one will have a rapid updraft, downdraft effect, and the second one will be just the opposite. These can be dangerous to you, especially if you've just become airborne. So, to avoid them, either lift off well before the intersection or hold your aircraft on the runway until well past the intersection. In both cases, the ground effect holds the vortex at ground level for up to 3 minutes. So, plan the same separation as for traffic on your own runway. Naturally, you must consider the normal flight factors in this avoidance and not try to lift off so soon you tend to stall out or to climb too steeply. At near stall speeds, you're already operating at near minimum control effectiveness, so even a slight wake vortex effect encountered could be disastrous. In the takeoff environment, there are 2 other situations to discuss: the formation takeoff and the MITO takeoffs. In formation takeoffs, if you remember, the vortices come off each wing near the tip and go backwards and downwards, spreading only slightly. Then you'll know how to avoid the hazard. Simply maintain proper position. Never drift behind your leader. If you should, during the takeoff roll, there will be no effect, as a vortex does not form until rotation. If you drift behind after rotation, move out, then rejoin in the proper position when airborne. In minimum interval takeoff, MITO, conditions are perfect for vortex encounters, as you can see. To minimize the possibility of encounters, as soon as you're airborne, move away from the aircraft ahead of you, preferably upwind. Okay, we've got you safely off the ground. Now, what steps should you take during climb out? You naturally are on the watch out for other aircraft on a collision course. You should also watch for other traffic which you will have to fly behind and or below. A jumbo jet entering the traffic pattern, although not coming anywhere near you, leaves a vortex behind his aircraft that is descending about 500 feet per minute and which will persist for about 3 minutes. So, if necessary, change course to avoid these areas. Of course, as you get further from the ground, you increase your chances of recovery before impacting the ground. But be safe. Avoid those areas behind and below. After climb out, while in flight at altitude, there are 2 situations where you're likely to encounter wake vortex hazards. These are during formation flying and during aerial combat maneuvering. During formation flying, you must be especially careful because of the proximity of other aircraft. Several months ago, we had an incident where the number 2 T-38 slid in behind the leader too far, caught the vortex, and was flipped into number 1. The pitot tube caught the horizontal stabilizer of the lead 38, resulting in damage to both aircraft. Again, visualize the path the vortex makes coming back and down from the wingtips. To avoid them, maintain proper position. If you can't, move out. The only time you should be behind another aircraft is during crossovers. Then follow proper steps and drop straight back and down, and only then slide across below the vortex. Notice on the film the position of the leader. If we freeze all positions, then we can draw in the leader's vortices. These are the areas that you must avoid. As you rejoin again, execute properly. Be sure you're outside the leader before you start forward and up. Join-ups are a very vulnerable time, especially straight-ahead join-ups and rejoins, but If you visualize where the vortices are and avoid these areas, you'll be all right. The last area of in-flight vortex encounters we'll discuss is during aerial combat maneuvering, ACM. The big danger here is that the encounter may very likely be when an aircraft is pulling a number of Gs. Remember the formula? The G factor increases the magnitude of the wake vortex. Since you're following the path of the leader and trying to overtake him, your chances of encountering his vortex are greatly enhanced. Furthermore, if you encounter his vortex during a maximum G turn, you're very likely to exceed the stress limitations of your aircraft. If we stop the film here, we can then overlay the vortex to show you the area you should avoid. In fact, must avoid. So fly your courses to intercept, but only intercept the aircraft you're attacking and not his vortex. The last environment we'll discuss is the landing environment. Landing is a delicate situation at any time, as you have two factors working against you. You're approaching stalling speed and the Earth at the same time. Introduction of a third factor, wake vortex hazards, is an unnecessary danger. The situations are approximately the same as during takeoffs. You must be aware of the traffic ahead on your own runway, both taking off and landing, as well as traffic on parallel and intersecting runways. Oh yes, don't forget the traffic in the air around you. Back at the beginning, we told you about one such encounter between a T-38 and a stretch C-130 and the resultant loss of life in aircraft. So when it's your turn to land, you have to listen carefully to the air traffic controller in the tower. When the tower says something like, Talon 2-1, turn right, heading 270, you're at 12 miles final for runway 35, following a stretch C-130. Slow to your final approach speed now. He didn't mention wake turbulence. He didn't say it anywhere in the communication. You had normal clearance to land behind another aircraft. But all through that clearance, to a pilot who would think about it, there were warnings that there's a problem. A C-130, a bigger aircraft, it's on a final in front of you. You must be close to it, otherwise the tower wouldn't ask you to slow down this far out. Sometimes the controller says, caution, wake turbulence. But it's a responsibility of the pilot to recognize more than just the tower saying the magic word. The pilot must recognize that all the ingredients are there for an encounter with wake vortex. Suppose that happens to you. You know, there's a wake vortex down there, but you're on an IFR clearance. You've been cleared for approach. According to the rules, you're supposed to execute that approach. So what do? Well, according to our rules, you should request permission to change to a different approach or go around. If a pilot sees evidence of vortices on a parallel runway affecting other aircraft, he must exercise his decision to go around or vary his approach or his speed to compensate. For example, a C-130 lands at 110, but in your F-4 or T-38 going 155 or 165, you're crowding him on the approach. So proper spacing at 10 miles won't last by the time you get ready for a touchdown. You must recognize the different rates to avoid his vortex. The second thing is a type of approach to shoot. Let's say the C-130 ahead of you shoots a simulated assault landing. Steep glide path, very slow, high angle of attack approach. So he creates a nasty vortex. But you're in a T-38 shooting a level, long dragged-in approach at treetop level. If you continue, brother, you're asking for it. So change your approach or go around. To emphasize once again the dangers involved in encountering the wake vortex, here's an Air Force pilot who was lucky enough to survive a crash caused by wake vortex. He's Major Robert Evely.
I was flying in a T-39 with my instructor pilot. The weather was good and the tower had cleared us to remain in a closed traffic pattern for multiple low approaches. I began the final planned traffic pattern as a simulated single-engine pattern. On the downwind leg at 1,000 feet AGL, tower cleared our aircraft as number 2 in the traffic pattern behind a DC-10 located over the ILS outer marker, inbound to the runway for a touch-and-go landing. The instructor pilot restored normal power to the aircraft and told me to continue the approach as a normal traffic pattern. The downwind leg was extended to obtain spacing behind the DC-10 on the ILS glide path. The T-39 was configured for landing on the base leg. Gear down, flaps full down, speed brake retracted. I made a relatively level turn from the downwind leg to base and onto the final approach beneath the flight path of the DC-10. The tower cautioned us on base leg and final approach of possible wake turbulence, and the instructor pilot acknowledged. I began a shallow descent on the final approach. At approximately 450 feet AGL, 2 miles from the runway, the aircraft tried to roll to the left, and I didn't let it. The nose pitched up slightly, and then it rolled violently to the left to an estimated 120 degrees of bank. Recovered to a wing level attitude, and immediately rolled violently to the left again in a descent. The aircraft recovered to a wings level attitude just before ground impact. We hit and bounced once, then plowed through a wheat field. We spun around to the left, skidded backwards, and came to a stop with a cockpit full of dirt. We shut down the right engine, but couldn't shut down the left engine because the throttle linkage was jammed. We couldn't open the main entrance door, but we were able to get out through the escape hatch. The rescue unit picked us up within 7 minutes and took us to the hospital. The instructor pilot had a spinal compression fracture, but I wasn't injured.
Thank you, Major Evely. Your experience in the T-39 reinforces our theme. Be aware of wake vortex. Recognize wake vortex dangers and avoid wake vortex. And you other pilots, don't think that because you're in a heavy aircraft you have no problem. And of course, fighters and trainers have even more of a problem. So, don't be a Flegel. Wake vortices are dangerous. Avoid them.